Today I'm going to talk about this paper, Sorting Out Lipschitz Function Approximation. The paper has a couple of motivations. I wanted to start out really big picture. I have some slides in this presentation that are sort of trying to cram a semester's worth of statistical learning theory into a couple slides. And I did that not to convey that knowledge to my audience necessarily. It was kind of an exercise for myself to just actually go back to the basics and make sure I understood it. So really high level, the idea is to reduce generalization error and increase adversarial robustness. This is like the high level problem they're trying to tackle. They also talk about some stuff I'm not so familiar with, like Wasserstein distance and things like that. I came across this paper because I've been interested in the fusion of, or the intersection of symbolic reasoning, deep learning, solving discrete optimization problems. Up until now, I kind of had this impression that deep learning had these glaring weaknesses, like it couldn't do something fairly straightforward like sorting a list, despite its pretty impressive capabilities in other areas. So I didn't think that it could do that. And a buddy of mine was like, well, actually, yeah, it can. You should check out this paper. So that's kind of how I got here. All right. Time to just quickly do a whirlwind of statistical ML, just to get kind of notation on the board. So generally, we assume there's some input domain X, there's an output domain Y. Frequently, to derive theorems, we assume that Y, the labels, are just binary, 0 or 1. And not all points in X are equally likely. There's a data generating distribution D that samples points from X. And there's a labeling function F, which takes points in X and labels them with something in Y. For now, the set 0, 1. There's a loss function. And again, like in early basic theorems, you just kind of assume it's 0, 1 loss for simplicity. You have a training set S, which consists of this series of tuples, point X, and then f of X, which is its label. Models, like neural networks, are just functions. The set of all possible models is called the hypothesis class. It's like, for example, if I'm using ResNet 50, the hypothesis class would be the set of all parameter configurations for ResNet 50. A single model is what you try and get through optimization. It's a single lowercase h in that hypothesis class. So training is basically just trying to approximate f, the labeling function, with some h. So I'm searching through this big stack of hypotheses to find lowercase h. And generalization error, this is the overall error, this is the expected error, the expectation of the loss over D, so over the whole data generating distribution, minus the loss on the training set. So I'm sure that most of this is extremely obvious to you all, but again, it was just kind of an exercise to go through and make sure I understood some stuff. Going one step deeper, a couple important notions to keep in mind. There's sample complexity. So this is a function, actually these are open intervals, but it's a function from 0, 1 cross 0, 1 to the natural numbers. And the sample complexity just asks, how many samples do I need to be within epsilon of the truth with probability at least 1 minus delta? So going back to the generalization error, if I want my true, my LDH, this thing, if I want the expectation of the error to be within epsilon with high probability, how many samples do I need to guarantee that? Then there's the notion of VC dimension. This is the largest size of a data set C, which is a subset of X, such that my hypothesis class shatters it, and shattering just means I can label it every which way. To make that concrete, the size of the restriction of H to C, so this is all the ways H can label C. I can shatter this thing if the size of the restriction of H to C is just 2 to the C, or you can replace 2 with the size of the output space Y. And generally speaking, the more parameters you have in your model or your hypothesis space, the larger the VC dimension is going to be. So neural networks with tons and tons of parameters may have a very high VC dimension. It doesn't always correlate with the number of parameters. So in Understanding Machine Learning by Shalep Schwartz and Ben David, which is like my Bible for statistical ML, they give the counterexample that even something really simple like a sinusoid function with this ceiling nonlinearity applied to it, even this thing has an infinite VC dimension because you can basically crank up the frequency so that you hit the training points with perfect labeling. Okay, I know I'm kind of babbling a lot about statistical learning theory, but we're almost done. I kind of just, again, I wanted to do this to contextualize the actual problem that they're trying to solve in this paper. So 2 more ideas. There's the growth function, tau, with respect to a hypothesis class. So this just asks the question, how many ways can I label this small data set C with my hypothesis space? And what happens is I change the size of C as I go from like, a data set with 1 point to 2 points, 10 points. How many functions are there that my hypothesis space can represent? So you can shuffle symbols around for quite some time and prove the following textbook generalization error bound. The gap in the overall risk versus the risk on the training set. This gap is bounded above by this quantity here. And tau h is in the numerator, which depends, in fact, on the VC dimension. And the number of samples down here is in the denominator. So if I want to decrease my generalization error and get a tighter bound, I can basically do 2 things. I can lower the VC dimension of my hypothesis space, perhaps by choosing a simpler model or reducing the number of parameters or layers or something. Or I can get more samples. So these are kind of 2 sides of this inequality, but generally we want to make this as small as possible.
Could I ask a question, Ben? On your first paragraph up there with that M sub h epsilon delta, are we supposed to have some kind of intuitive feel for what the shape of epsilon delta space is?
An intuitive feel for what that space looks like.
Yeah, well, so you have epsilon within the truth, and then you have with a probability of 1 minus delta. So I'm just trying to get what the relationship is between those. You've got this functional relationship. I'm trying to figure out whether that's if I plotted, M of h as a function of epsilon and delta, is it just some kind of smooth thing, or is it there's all sorts of gotchas in there?
Yeah, I mean, fair question. The way I would think about it is that there's a trade-off between epsilon and delta. So if I just need my risk to be like barely above chance, I can have like, epsilon is my error term. So if the error can be really high, I can guarantee that with probability almost 1. So, delta can be really, really small. On the other hand, if I want an error to be really, really small, I may have to start sacrificing my probability. So if I want to get 100% accuracy, may be possible, but with very low probability, I'm going to find that needle in the haystack. And you can kind of go the other way too. Like if I relax the probability bound, well, I can have perfect accuracy. I can guarantee that as long as I'm allowed to do it, a low percentage of the time.
Okay. I guess maybe I'm anticipating the Lipschitz condition, but with the question I have, just trying to kind of visualize that your Cauchy as a form of trade-off, but I'm presuming it's a nonlinear trade-off of some sort. So so I'm just kind of wondering if there's anything interesting in the shape of that trade-off.
It's a good question. I've never stopped to try and plot a sample complexity bound. So I don't know that I can give you a whole lot more, honestly.
Yeah, because when I see the Lipschitz condition, there's usually some implied in other contexts, some that the surface is continuous and is locally differentiable and a couple other interesting things. So I was just trying to kind of map that philosophy to what you were showing there. But anyway, why don't you
Yeah, I'll
just
get
go
there.
on.
It's a little bit different. I mean, the Lipschitz thing is going to be with respect to the function that you're learning, like the H in the small h and big H, the actual, neural network that you learn. We're going to look for something that has a network, a function that has a Lipschitz property, which is a little different than sample complexity function and the smoothness or whatever of this.
Okay, fair enough.
Okay, promise, last slide on theory. The way I like to think of this to try and make things concrete is by thinking about how many functions I have to search through or how many samples I need. So if I take some data set C with, let's say 10 points or whatever, there are going to be, and if the labels are binary, there's going to be 2 to the 10 possible functions between the two. So this is just a general formula to keep in mind. Now, how many functions can my hypothesis class represent from this little data set C to 0, 1? It depends on the VC, the VC dimension of your hypothesis space. And for a neural network with a really large number of parameters, the VC dimension can be high. So the question is, doesn't this mean that the generalization error bound increases? It does. And so there's also kind of an interesting question here of yes, neural networks overfit, but shouldn't they actually do even worse than we see in practice? So just kind of an interesting thing to keep in mind. And I made this slide to try and tie together 2 notions. There's the notion that as I add more parameters to my model, the function space that I have to search through gets larger. So that hurts my generalization error. On the other hand, there's what people always refer to as the curse of dimensionality, which has to do with the dimensionality of X. And everyone just knows that as I increase the number of dimensions, I need more and more samples to cover that space better. So how are these ideas related? It's a good exercise to sit down and kind of walk through it. So here was kind of my thought process. If I discretize my space X into bins, so for now, imagine X to just be the interval 0 to 1 on the real numbers. And I want to chop that thing into bins. So let's say I chop it into 10 bins, 0 to 0.1, 0.1 to 0.2, and so on. The question is, how many samples do I need to construct my data set C? Well, obviously, if it's just, one-dimensional, I need only 10 or, n bins, 10 samples. But if I take that interval 0, 1 and, turn it into a square, so now I've got 0, 1 cross 0, 1. Now I've got the product of those 2 kind of sets of bins. And that means it's going to be 10 squared, which is 100. And then if I turn that into a cube and scan back and forth, it's going to go up to 10 to the 3 or n to the 3. And so generally speaking, with k bins and dimensionality d, the size of this data set C, which samples 1 point in each bin, this thing scales exponentially. So that means if I want to construct a data set like this, the size of C is exponential in D. And finally, to tie this back to the problem of how many functions there are, that means if I go back up here and construct such a data set, the number of functions is exponential in the dimensionality of the inputs for a data set of this type. So the takeaway is basically the number of functions I have to search through is going to grow in 2 ways. First of all, it's going to tend to grow in the input dimension and in the number of parameters. So both of these things will tend to hurt the generalization error bound. So I started this presentation by saying the whole problem that they're trying to tackle in this paper, one of the main ones, is lowering the generalization error. And they're these two problems with generalization error. There's how many parameters you have, and then there's the dimensionality of the inputs. And I just wanted to kind of tie them together as part of the same coin about generalization error. So that's all I have on learning theory. Does anyone want to respond or have like questions about this before I get into the actual paper?
So that's the space that's kind of, you know, exponential in two fashions. But that's like the total space. If are there priors that reduce the effective dimensionality of that space that we're going to be talking about, or is that a question for a different day?
I'm going to touch on it right here, and I'll tie back. So you're right. So generally, like this is just 2 to the size of C functions. Okay, how do I restrict? So instead of having to learn every possible function here, I don't have to search through every function. So here are some strategies. One idea is to assume that the labeling function or the target F has certain properties. One would be to assume that it's like invariant to certain changes in the input. So we've all talked about invariance recently, but you know, obviously the idea would be if I'm trying to detect like, is there a dog in my image? If we want translation invariance, it shouldn't matter where the dog is in the image. It can appear anywhere. The labeling function should be invariant to those types of changes. Another one would be maybe the labeling function has a small Lipschitz constant. So the labeling function is really, you know, from the input domain to 0, 1. So like, what's Lipschitz got to do with this? Well, if we just assume there's like a continuous Lipschitz function and then we threshold it to get the labels, you know, we can think about the underlying F as having a small Lipschitz constant. So that also restricts us down from having to learn, you know, all possible functions to like a smaller set of functions. Another one would be to assume that the labeling function only makes use of a subset of the features in X. And then we can try and learn functions that respect these properties. And I have noted here, remember how many functions? This will help us decrease the size of the function space we have to search through. Maybe to put a finer point on that, if we go back to the growth function tau, this thing is going to grow exponentially as long as my hypothesis class shatters C. So if I want to slow down the growth function, a couple of things can happen. I can either increase M or I can decrease the size of my hypothesis class. There's a theorem which basically shows that as soon as you exceed the VC dimension of H, the growth function goes from exponential to polynomial. And so if you have enough samples, then the growth function slows down, or if I make the VC dimension smaller, the growth function slows down, which gets back to your point, Kevin, of like, now I don't have to search through exponentially many functions. Now I have to search through polynomially many functions.
And I just want to make one comment. The reason why I was going there is that there was a problem in computer graphics of in ray tracing where you're trying to, there are a lot of variables when you're trying to launch rays, that how many samples do you fire for anti-aliasing, how much do you do for detecting shadows, how much for detecting depth of field, and there's like n dimensions that you're trying to go across. The critical thing that made ray tracing work so well was the fact that they found out that they didn't have to increase the sample size with the dimensionality. They just simply scattered the samples across all dimensions independently of each other, and that was sufficient to sample the space. So this is giving something of a bound, more detail from that finding, that you're able to actually do something like that and still, you know, sample that space. So that's what intrigued me about the thing, is that's something that came up in the 1980s, and the math was too complex for me to understand at the time, but you presented a nice background for that.
It's a very nice tie-in. Yeah, so I mean, as I'm digesting it, I'm just sort of thinking, how many samples do I need so I can, is the question, or was the problem like, how many samples do I need to learn a function that like shades properly and like represents these different aspects of computer graphics properly?
Yeah, that's essentially it, because you basically you have to launch enough samples so that you simultaneously minimize like aliasing and all these other aspects, and including distributing samples in time so that you can get motion blur. So the worry was that you're going to have to, go up, again, exponential number of samples, because, well, you want to sample each of those dimensions equally, right? And it turned out no. After a certain number of samples, it actually, I mean, maybe it's that cut point where you said it went from exponential to polynomial. I'm not sure, but the finding was that no, you just have to launch a sufficient number of samples, and the rest of the error converts into a form of noise which is acceptable. So
Yeah.
it somehow, so that's one of the, it just kind of solved this huge dimensionality problem that they're having and made ray tracing practical.
Yeah, it's a very nice tie-in. So I'm trying to relate to that to kind of like the properties of the target function. And like there are kind of two ways I could unpack what you're saying, or two kind of guesses I have about this. Like one would be of all those dimensions, like motion blur and like shading, and I have no idea what I'm talking about with computer graphics, but with all of those things, one possibility that would make it tractable is that some of these dimensions matter a lot more than others. So I can sample some of them heavily, and some of them I just don't really need that many samples and it doesn't hurt me. Or another possibility is that, like you said, if they're sort of independent of one another, then I don't have to sample, like for 2 dimensions, all pairs of points in a grid, or like all triples of points in a cube. I just have to actually sample each dimension, n times, and then the complexity would be linear in the number of dimensions instead of exponential.
That would make it polynomial, right? But they found out that it actually was more or less linear.
It's a good tie-in. I'm glad you brought it up, because it's nice when the ideas here actually feel tangible and they relate to like a real world problem. Okay. Yeah. So the other thing that they talk about in this paper are adversarial examples. I'm not an expert. I'm not even really a beginner in adversarial machine learning. And this seems to be a pretty deep field. And the person who notified me of this paper studies adversarial ML. So I'm tempted to say this is through the extremely blurry, probably largely wrong lens of generalization error. But anyway, the sort of definition roughly of an adversarial example means I can apply a small perturbation. For example, the norm of the noise that I add has to be small. I perturb the inputs X by a small amount, and it changes the decision rule. So basically the label that the model spits out from, in binary classification 0, 1, but in multi-class cases, it just means it flips it to the wrong answer. So naively, not knowing anything about adversarial ML, it's part of the generalization error. So all of those examples that you get wrong, some of those are going to be due to adversarial examples, like cases that look adversarial. Then some of them are going to be cases that are not, but you just still got them wrong. So all other things equal, if I just make my model more adversarially robust, then theoretically I should decrease my risk. Another kind of just thing to note is that from what I can tell, adversarial vulnerability is generally observed in these really large models with a high VC dimension, and not so much in small models like an SVM or something. Again, I'm not an expert in this domain, but my naive read of this problem would be something like adversarial vulnerability is a symptom of the fact that you've got a really high VC dimension, and so the generalization error has the potential to be pretty high.
Hey Ben, by the way, I worked in adversarial AI, machine learning, and yeah, you characterized it well. Yeah, that's all correct. And regarding the difference between the vulnerability to the other kind of generalization errors, right, from like misclassification, those sometimes are not directly eliminated by making it more robust to adversarial attacks, because those adversarial attacks tend to be more obscure, right? You change pixels and in a random way that's not even noticed, and you want to do it in a way that's not noticeable, right? You have a very small epsilon on the pixel. Either you do a small epsilon on the pixel value you change, or you do a few amount of pixels you change, right? There have been examples with one single pixel, can I change it? So those are a bit different in nature than just mistaking a banana for a cup or whatever. And so yeah, so you don't necessarily get a better performance by making it more robust. Actually, what happens in practice is that with these various techniques to making it more robust, typically you lose some classification performance. So there's some trade-off, right? Making it robust, but then you lose some of the performance.
Yeah, not to derail into adversarial ML, which is going to be pretty much speculation for me, but I've heard both kind of takes. I've heard that there's a trade-off between your performance and how adversarially robust you are. But I've heard that in some cases, like surprisingly, making it more robust actually also increases just overall accuracy.
In some cases, yeah. Depends what the kind of errors you make. Yeah.
Okay. Basically, the read that I have on this is that it's just relying on theory here. The number of functions that your hypothesis class contains is extremely large. And that means the number of functions that fit the training data well, but don't fit the test data well, is also extremely large. So the kind of naive interpretation is that I'm just selecting a hypothesis from this hypothesis space that fits the data, but it's basically my guess would have been it's a type of overfitting. So I don't know if that rings remotely true, but that would be my naive model of what's going on. Oops.
Yeah, there's certainly some amount of overfitting.
Okay, so now let's actually talk about the paper and Lipschitz functions. Here's the definition of a Lipschitz function. My x and my y both need to be metric spaces, and d is like dy is a metric in the y world, and dx is a metric in the x world. And a function is Lipschitz continuous if there's some constant k, so that over the whole kind of domain x, this difference, the distance between f of x1 and f of x2 is always bounded by this k times the difference in these inputs. So mentally, you start shuffling symbols around. You're kind of like, okay, I've got dy dx on the left-hand side if I divide both sides by this. So kind of the intuitive way to grasp this for me is just that the slope is less or equal to this constant at all times. So they're trying to learn a neural network that is that has this Lipschitz property because it narrows down the space of functions that you have to choose from. It makes your hypothesis class a lot smaller. And this has benefits, including possibly reducing generalization error, providing guarantees about adversarial robustness, and maybe even making it more interpretable. Okay, a little bit of math.
Can I ask one quick question back on that slide? Do we know of problems where we can't guarantee that continuity, or is it's always possible? You just basically try to construct solutions that do satisfy that property.
No, I think it's the opposite. It's that with generally speaking, this is not satisfied. Like when you learn a neural network, I think generally there are no guarantees about Lipschitz whatsoever, and trying to make it satisfy this is trying to make the function that you learn Lipschitz continuous is like a somewhat new line of research.
Okay.
That's my take.
Thanks. Yeah. Okay. Thanks.
But by the way, Ben, what do you think makes it discontinuous? Since generally Lipschitz, we're not talking about a small k, right? K could be very, very large. And so it means if it's not Lipschitz continuous, there's some discontinuity, right? Some gap, some jump. How do we get the jump in?
Why do you think? Yeah, I mean, my intuition here would be that like adversarial examples suggest that functions that are normally learned are not Lipschitz continuous because a small change in the inputs flips the label. So it could be that you're already it's not actually a big change in the logits of the network, but
because it's like a one-hot vector and we just choose one, like the best. Right.
Yeah. So
yeah, okay.
Do you agree with that?
Yeah, that's right. On the output, yeah. Since we only choose one correct sample, one correct class, and we know a small change at some point, it flips the class. Yeah, yeah, right.
Actually, yeah, now that I'm remembering, I think there are plenty of examples where an adversarial perturbation also causes the logits to change a lot. So instead of being like very confident that I'm looking at a dog, the logits can flip to being like really confident that I'm looking at a cat. So I think that's a clear example of not being Lipschitz continuous. Or it means that K is just really, really large.
Yeah, K is large. Yeah, in that case, it would be continuous, but K is large. But then at some point, if I do the threshold, right, this is this class, that's where I get the discontinuity.
I see. I'm sorry. You were asking about why do I think it's discontinuous, and I don't necessarily think that for like the logits. I'm more just thinking that K is large.
Yeah. Right. Okay. Good. Thanks.
Okay. So they just casually mention in this paper, one Lipschitz functions are closed under composition. This paper took a long time because I had to like stop and like convince myself of a bunch of things. So that also means I ran out of time and didn't get every theory in this paper, but I've never like taken a class on functional analysis or anything. So I wanted to take this opportunity to try and think through what they mean by this. So generally, this was just my naive reasoning here. I have two functions, f1 and f2. And let's say they have Lipschitz constants C1 and C2. That means this is just the definition of Lipschitz continuity. The left one has a constant C1, the right one has a constant C2. And if we assume that this distance metric, excuse me, has the property that in the limit as x1 minus x2 goes to 0, that if I divide both sides of this inequality by this distance in the x's and get this, in the limit as x1 minus x2 goes to 0, I recover the derivative of this function. And I think this would be true for a distance metric like absolute value. So if that is the case, then what that means is I can say, well, d dx for this function is less or equal to C1, and it's less or equal to C2 for this function. And that means if I compose the functions by the chain rule, I get the derivative with respect to x of f2 times the derivative with respect to x of f1. And these are both bounded by C1 and C2. So the composition of Lipschitz functions has Lipschitz constant the product of the two functions. Maybe Heiko, if you or anyone else really, if anyone's familiar with this, you could maybe check me on this and see if this reasoning is accurate or if there's a hole in it.
That's a good reasoning. Yeah.
Okay, cool. So if this bullet point is correct, then if C1 and C2 are both 1, then the composition of 1 Lipschitz functions is automatically 1 Lipschitz. So when they just mentioned that in the paper, I didn't get it initially. So I thought I would try and like go through and actually get it.
The 1 Lipschitz means that's the K. Is it K equal 1?
Yes.
Is that the notation? Okay.
Yes. I used C here. I probably should have used
Okay,
K.
I see upstairs. Yeah, in the first line it says C1 Lipschitz. Okay.
So when you mentioned this function, that includes whatever nonlinearity is in the layer?
Well, everything above this last bullet point, we're not even necessarily talking about a neural network. We're just talking about functions, generally speaking.
Mm-hmm.
Right. So it's the bolded one that where you're basically saying that you're connoting a MLP layer to being a function in the same with the same properties as you're trying to apply in the preamble there. Is that the case, that you consider a whatever the nonlinearity is, you consider an MLP layer to be a function?
Yep, that's exactly right. And you nailed it. It's like to make the whole thing, the whole function, the whole network start to finish 1 Lipschitz. It means that like the weights in each layer need to be 1 Lipschitz, but then the nonlinear activation also has to be 1 Lipschitz, and they tackle both aspects of that in this paper.
Okay.
Yeah, so yeah, I mean, that's exactly it. So now this problem of making the whole network Lipschitz is boiling down to, I need the weights to be Lipschitz and I need the activations to be Lipschitz. I'll skip that slide for now and come back to it if necessary. So here's what I understood from the next section in the paper. If the weights W, so not the activations, but just the weights here, if these are norm constrained, then I have a Lipschitz function. The reason is that having the norm constrained is a stronger condition than being Lipschitz. So if I have a function that's 1 Lipschitz, that doesn't necessarily mean that the slope equals 1 everywhere. It just means it's less or equal to 1 everywhere. So the ReLU activation, for example, that is definitely Lipschitz almost everywhere. It's not at the single point where you cross 0, but that point has measure 0. So almost everywhere, ReLU is 1 Lipschitz. But on the left side of 0, you have no change going on. So the derivative is actually 0. And so you're less than 1 Lipschitz there. You're 0 Lipschitz on the left side of the real numbers. So if I constrain the norm so that basically when I multiply by X, the norm of the output Y is constrained to be 1. Now I'm saying that I have to be Lipschitz 1, exactly 1, like everywhere. I can never even be less than 1. Does that make sense?
Yeah, question regarding the definition of Lipschitz 1. Does it mean, it doesn't mean it has to be 1, right? It says just the K is 1, right? Isn't it like the upper limit?
Yeah, exactly. K is the upper limit.
Yeah.
So it took me a while to parse this, but I think what's going on is that that's why ReLU it's 1 Lipschitz.
Mm-hmm.
But if you just looked at the left side of the function between -infinity and 0, it's 0 Lipschitz on that side.
On its own, yeah. But the whole thing is still 1 Lipschitz, right?
Exactly.
Smaller than 1, yeah, okay.
But if I make the norm so that I multiply x by w, and the norm of y is always fixed to be 1. Now I've just made it so that the slope has to be, I've made it so that the slope basically has to be exactly 1 everywhere, not just less than 1.
But by the way, I'm not quite sure the definition is. You mentioned for the Rayleigh around 0, it's not Lipschitz. But isn't it, if I take any delta, if I think about the function y over x, right? For any delta y divided by delta x, right? It's always bounded, right? It doesn't have a derivative. It's not, you cannot derive it at the point 0, right? But it's still Lipschitz, isn't it? Because it's always bounded.
But the slope is discontinuous.
Yeah, it is. But maybe that's a question how exactly Lipschitz is defined. But isn't it, it has to be bounded? It doesn't need to be.
Well,
continuous.
if the definition where they were showing where we were trying to approximate a partial derivative with the finite derivative, and it's ambiguous at a point, then it's a singularity in that sense.
Yeah,
That
if the function is the derivative itself, right?
Right, but the criteria that they were defining there, if you're saying, if I approach it from the right-hand side, I'm going to have the Lipschitz 1. If I approach it from the left-hand side, I'm Lipschitz 0. So at that point itself, you have a conundrum. So it's continuous in some sense, but the derivative is not. So what impact that has on Lipschitz continuity is, I guess, what the question is.
I mean, I think you raise a good point, Heiko. I was thinking that it wasn't Lipschitz at that one point, but actually going back and looking at the definition, the changes in, this and this, if I move this around,
Yeah.
seems like it's,
Right.
it might actually still satisfy this upper bound. So it's like Lipschitz continuous, even though it's not like actually differentiable at that point.
Yeah, differentiable is more, how do you say, stricter. Yeah. Yeah, if the F is the Rayleigh, right, then it is continuous, Lipschitz continuous.
Okay, I think I learned something important just now. Differentiability is a stronger condition than Lipschitz continuity.
Mm-hmm.
Okay, so back to the idea of making the weights and the activations one Lipschitz. A stronger condition is that they're norm preserving, gradient norm preserving. But wait a minute, if they're norm preserving, that means the slope is just 1 all the time. And doesn't that mean I just have a linear function now? So now they have a couple theorems about this. They say that if I have a whole function, a neural network from Rn to R, and the weights are always 2 norm constrained to be less or equal to 1, then the norm of the gradient is 1 almost everywhere, then the whole function f is linear. So a little bit to unpack, but I think the general idea here is that as I add these constraints, that like the norm and the gradient norm therefore have to be not just Lipschitz, but actually exactly, well, actually, I'm not sure. They use less or equal to here, but for the gradient, they say the gradient has to be exactly 1. But I think this is not obvious. They prove a theorem about this, but I think the high level intuitive view is that these constraints basically take your network and cause the nonlinearity to disappear. Okay, so next, this is quite dense, I'm realizing. They prove another theorem. I'll just read it to keep everyone on the same page. So we have this network from Rn to R, and it's built with matrix 2 norm constrained weights, and the gradient is always equal to 1. Then without changing the actual computation of the neural network, I can replace all of my W's with some W tilde whose singular values are all equal to 1. And when I read this, I was kind of like, well, wait a minute, if the singular values are all equal to 1, that tells me it's stretching and squishing space equally in all the different directions that W is warping space. And I guess they show something kind of similar in the proof. They basically say that depending on the dimensions M and K, you either get orthonormal rows or columns. And when they're the same, then W is orthogonal. And so, like, yes, indeed, that means that the rows are all warping the space in different directions. Yeah, I'm not sure I really get what's going on here, but like if you blur your eyes a little bit, it seems like it makes sense. Okay, so now on to activations. So I guess the whole point of all these theorems is that, first of all, instead of searching over W, I can search over W with singular values that have this the class of matrices with singular values all equal to 1. And this helps with searching over W's. And then for activation functions, they have a couple of notes. First of all, they note that most activation functions like tanh and relu are already 1 Lipschitz, or if they're not, you can do some scaling to make them 1 Lipschitz. So relu is Lipschitz, but it's not norm preserving because when you're on the left side of 0, the gradient goes to 0. And so it doesn't preserve the gradient norm. So the whole function is no longer going to satisfy that gradient norm preservation property.
Right. Maybe a question here, might be something I missed. Why do they care about this norm preserving as opposed to just 1 Lipschitz?
Yeah, my guess about that is that norm preserving is a stronger condition than 1 Lipschitz. So,
yeah, it is. But why do we care about
it? Because it means that if I'm trying to learn a Lipschitz function, if I can restrict my W's to norm preserving W's, I have a smaller space of W's to search over.
Right. Is there the motivation here? You just want to limit the search space.
Well, and it's also, actually, I don't know that that's really the motivation. I think it may just be hard to guarantee that the whole function is 1 Lipschitz. So you might consider several strategies, and the strategy to ensure that it's 1 Lipschitz here is to focus on norm preserving W's.
Yeah, okay, interesting. Maybe the concern is you could have some parts, right? If you think about DeepNet, right, it collapses to almost 0 W, and then you would sort of at another layer need to blow it up, right? They probably want to avoid that. This way, it's nicely, if you go deeper, right, it nicely stays sort of the same norm. Maybe that's the reason.
They do talk about that later, that like because the norm is preserved, then the gradient norm is preserved. I think that follows. But
Yeah.
if the gradient norm is preserved, then you can stack as many layers as you like and you won't have vanishing or exploding gradients.
Right, right.
So this seemed like a bit of a conundrum to me. It's like you're looking for a nonlinear activation function that's norm preserving. So the slope is 1 everywhere, but then you're just kind of like,
It's linear.
Isn't that just a linear function? So what's going on here?
Right.
Okay, so here's how I interpreted this. First of all, actually, no, let's go to the next slide. So this is a nonlinear activation function that they introduce in this paper, and each cell here is a neuron. And what they're doing is they group these neurons into clusters of, say, 5 in this example. So like here's 5 neurons, here's 5 neurons. And in each of these windows, they just sort the neurons based on their pre-activations. So this is still not intuitive, because when I saw this, I just thought you're sorting, and sorting can be like for any inputs that look like this and outputs that look like this, I can do that with a permutation matrix. So am I not just multiplying by a permutation matrix, making the entire thing linear once again? And that's where the kind of almost everywhere thing seems like it might matter. They do show that they're able to learn functions like absolute value, or chopping it up into W's. And it seems like the network basically has this one linear function over here, and it doesn't have to worry about this one point. It can have another linear function over here. Maybe now it's also a good time to look at the actual paper. Let me make my participant a little smaller. Okay, running short on time. So they try and provide some intuition for like why this is a nonlinearity in the appendix. Pretty interesting. Still not really sure I get it yet, but they show, so min max, max min, this is when the window size is 2. So I just look at 2 neurons and I sort them. That's all I'm doing. They show that this is in fact the same thing as applying this ReLU versus minus ReLU minus X, this composition, this like mix of nonlinear activation functions. So they try and demonstrate that flipping my X's around basically can recover ReLU functions and different variations on ReLU. They also show that it can do the same thing as the absolute value function. I'll be honest, I've looked at this for a little while. I didn't quite get it. Seems like it's correct though. They can learn the absolute value. It can be the same thing as absolute value nonlinear activation. The other way to get some intuition about what's going on is they train the network to learn one-dimensional functions. And so this just means instead of like a vector, I just have a single number as input to my network, as a way of kind of diagnosing what's happening. So here are the inputs. And if I have a network with just 2 hidden units, then these are what my 2 hidden units are doing. And if I sort them, you can kind of see that on the right. Basically, the green and the blue, the 2 units flip on the left-hand side. So I get this. And with this network with one hidden layer of only 2 units and a one-dimensional input, they're able to read out in the output something that looks exactly like the absolute value function.
I'll just make a quick observation here. I mean, they ding the ReLU because of the fact that it's 0 in 1/2 space of the inputs. Have they just simply split the problem into 2 half spaces, one dealing with the negative inputs and one dealing with positive inputs? I mean, that, minus ReLU of negative X. So if X is negative, that makes it positive. That means it's positive, but then you give it a negative value. So you're just displacing it. And so I mean, have they basically made a bilateral ReLU? Is that what's happening here?
Honestly, I wish I knew, Kevin. You're talking about this equation right here?
Yeah. So that will admit to both positive and negative values of x, right?
Yeah, let's just walk through it. If x is positive, then x is going to be greater than 0. And that means x is going to be here and 0 is going to be here. So what's happening? X is positive, this is just x. Minus x is negative now. So that means
Right.
this part goes to 0. So that makes sense. Now if x is negative, then ReLU of a negative number is 0. So now I've switched 0 to be on top. And ReLU of minus, now I basically just get x here. And then I apply the minus sign to it. So I get, hey, wait a minute.
Negative value.
Yeah, you're right. But x was, no, x was negative in the first place.
Right. So then it becomes positive.
Oh,
in
you're
there,
right.
You
You're
apply
right.
ReLU to it, and then you basically, so.
But you could say it's x again, right?
Yeah.
It is, exactly.
So, I mean, it's like I don't know if it's the function of the sorting or what, but at least in this kind of toy example, they've split the problem into 2 pieces and it looks like they're dealing with them independently.
Well, I don't think they implemented it this way. I think what they're doing here is they're trying to show that this swapping of things around and sorting a couple of elements is like equivalent to it's like similar to other nonlinear activations.
Okay.
Mm-hmm.
But it's if you start out with x, now you go to a space where you have 2x. You've doubled the dimensionality. So in that sense, in the upper one, you're dealing with 1/2 space of x, and the other one you're dealing with the other half space of x. So you've doubled the dimensionality. Excuse me. Maybe dimensionality is the wrong way of saying it, but you've gone from a scalar to a 2 vector in this particular case.
Not sure I actually follow that. You have gone exactly from a 2 vector to a 2 vector.
Well, you start with x, right? If you just had x and did ReLU, you'd get a single value, right? You wouldn't get a column vector. But in this case, you're getting 2 outputs for every 1 in.
I think I kind of see what you're saying. I mean, you don't. They're trying to show that if I applied this function to this vector x and 0, it is the same thing as applying 2 nonlinear activations to just x.
Okay, I misunderstood. I'm sorry. Okay.
No, that's fine. Like, I mean, it's good to pick this apart because it's pretty confusing. I'm still not totally reconciled with the idea that you're basically just applying a permutation matrix as an activation function. And like, yeah, I still don't really get it, honestly, but
well, the permutation matrix assume that the sort order is constant, right? But you don't necessarily, for each individual thing, if you're doing a real sort, that permutation matrix is going to vary depending upon what the input is in order to get things sorted. So it's not a constant function.
Oh, is that the idea that basically it's non-linear because it's basically just a different permutation matrix at every time step?
Yeah, it's almost like k-winners. I mean, you're sorting the thing. You're breaking it up into parts and groups and then sorting each one of those things, and they have a canonical order based upon their rank. I'm not sure what happens after that, but that's at least. So it's if you had a static permutation matrix, you'd be exactly correct. But because it's a sort function, that's not the case. You're using ranked statistics on those pieces. You
Thanks,
could
Kevin.
implement it as such, but it change each time you change your input.
Yeah, I don't think I quite got that until now. I'll have to go back and make sure it really makes sense when I really get into it. But I think initially that seems right. Does that seem right to you, Heiko?
Yeah, I don't have a good intuition yet about how the sorting works.
Okay, well, we're actually already over time. So let me just try and kind of summarize now some results and ideas. So pretty much every machine learning paper that gets accepted somewhere, they had to do experiments that show that their method works well in some cases. So they do various experiments on like Wasserstein distance and looking at the Wasserstein distance between samples generated by GANs and like a real data set, and their method does really well. They're able to learn those nonlinear functions like absolute value or W, so they can learn zigzags and things like that with this. So it's pretty interesting. Going back to my original kind of curiosity about being able to solve discrete optimization problems, well, this is an interesting way that deep learning might actually be able to get a handhold or a foothold on that, because now you're sorting, the nonlinear activation is sorting. So it seems like you could probably sort a list using this technique. Like you said, Kevin, this relates to ReLU and K-winners, because K-winners just, you're sorting and then changing the threshold so that exactly K units are on at any time. So the relationship of group sort to K-winners is interesting. Throwing a lot of stuff out there, but I had never heard of this dynamical isometry property. Had you guys?
No.
I think what dynamical isometry means, I have to look more closely at the definition to be sure, but it's something about having the weights of the network all norm preserving, and that means the gradients are norm preserving, and that means like as you take optimization steps, the network continues to be norm preserving. So that's what I think it means. And apparently one paper showed that if you initialize the network so that the weights are norm preserving, this can radically speed up convergence and training. And I had not heard that until I looked at the discussion in this paper. And so that seemed like a pretty cool, interesting thread to pull on. And like you said, Heiko, if the gradient norm is 1, then you can stack as many layers as you like. So no vanishing gradients. Finally, they also prove something pretty interesting about being able to approximate arbitrary one Lipschitz functions using this method. So the math is a little involved. It gets into function spaces and like the Weierstrass-Stone theorem, which I have never looked at until I saw this paper. But anyway, these are just the interesting kind of threads to pull on that this paper alerted me to.
Interesting, cool. Did they show it on more like some complicated function, like nonlinear function, or well, they can learn it?
Just pull up the paper and look through it.
Did it amnest?
No, but this is just estimating the Weierstrass distance between like the real data and GAN generated data.
Yeah. Okay, so they did amnest, right? And then
yeah, you're right. They said they did MNIST and ImageNet and CFAR, I thought so, but I think they buried it somewhere in the appendix.
So
did it faces? Oh, okay.
So I have a quick question. So we have this conundrum where it says the slope is 1 everywhere. Well, if you're in 2 dimensions, that would be somewhat constraining. But what if you're how do you define the slope when you're in multiple dimensions? I mean, is it kind of, you look at, I'm just wondering if what they're doing is by making, requiring things to be orthonormal, whether they're kind of sitting on some kind of hypersphere where the local slope is one everywhere, but it doesn't mean that in every dimension it projects to being one. I'm just wondering if that's the degree of freedom that they're allowing themselves.
Do you have a good intuition for that, Heiko?
No, yeah, that's a good point, Kevin. I don't know at this point. Need to think about it.
I mean, if I run with that for a second, and if you basically look at, their condition for initializing the weights to be orthogonal, if you wish, you've kind of collapsed the dimensionality down. So now you're sitting on a manifold that's orthonormal, as opposed to all the various other combinations in. So maybe it has really good properties that you're starting out, making sure that each of the columns of your matrix are pointing in different directions. And that they're actually capturing some independent aspect of your input.
Yeah, so the matrices is essentially you have let's say if it would be a square matrix, is all the eigenvalues are all one, right? And it's like an identity matrix.
Well, if the eigenvalues are all one, then it's n ways degenerate, right? So
yeah, it's just a rotation, right?
Yeah. So that's clearly you've cut down the dimensionality if that's the case.
But it's not going to be just a rotation if the matrix is not square, because then the singular it's only that case because singular values are the same as eigenvalues when it's a square matrix.
Yeah,
I think the singular values are different when it's not square.
Yeah, the definition of singular in that case, you've got to go to what, pseudo inverse or something like that in order to make sense of that.
I think that's right. And so I think, it seems right. Like then you get.
Yeah, so only to down project and then rotate. Yeah, something like that.
But it's an interesting space to play in if, in fact, they found some more principled way of assigning the weights. And then you have the interesting notion of, okay, what if your weights are sparse? What's the implication then?
Okay.
You're projecting to different subspaces, maybe? I don't know. I mean, the matrix itself is going to be singular, maybe, depending on, I don't know. No, that's not true. I'll take that one back. But it would be interesting to work through the thing is saying, okay, you create this dense matrix, it's got these properties that they claim is really good. Now, how can you add zeros to that and still preserve these nice properties that they claim are you want to preserve? Is there some kind of interesting principle that you can say how we assign our zeros to continue to get these nice properties?
Yeah, I think if you think about in terms of the square matrices, so then essentially have rotations, and to get zeros and ones, then you have only 90-degree different rotations, right? So it would be a very limited set of rotations.
Well, it's almost like you're projecting into subspaces then when you put the zeros there.
Yeah.
So you're
Can it also
collapsing.
be permutation matrices? Those would have eigenvalues of 1 and they can be square.
Yeah.
Yeah. Okay. Did you understand at the end what the Wasserstein distance is about?
No, that's going to be, well, yeah,
Well,
that's,
that yeah, Wasserstein distance is optimal transport. So typically, it's the Wasserstein distance between two probability distributions, and it sort of measures instead of like you probably know the Kullback-Leibler divergence measures the distance between the distributions. So for the Wasserstein distance, it's like the amount of transport, let's say these are the two distributions, the amount of transport it takes to make them overlap, or as much
So
overlap as possible.
the other name for it is the earth mover distance. So if you imagine a
Yeah.
bulldozer kind of, pushing values from one bin to another bin, that's how much energy does it take to make the one distribution match the other one?
Yeah, and the nice thing is, yeah, we worked with Wasserstein distance in the past. So the nice thing is, for this compared to Kullback-Leibler divergence, is you have a very good distance measure, even if they're very far apart from each other, right? You have a nice gradient for the distance measure. And otherwise, right, if you have two Gaussian functions, they're far apart, so the overlap is almost zero, and then you get very bad gradients. And so for something where you need the distance between distributions, Wasserstein distance is nice for numerical reasons.
Nice.
Yeah, Ben, regarding the results, what were the results on the cipher and the phases? What did they report compared to other methods?
Go back to it. I actually didn't look at it.
Is
It's
that
like
table
at the
5?
very end of the appendix.
Yeah, it's on table 5. Okay. So they have, this is MNIST. Yeah, okay. The cipher is, which one is theirs? Oh,
It's going to be
the cipher.
this. Because, okay, so I didn't even talk about this technique in the paper, but the technique they use to actually make the weights, not the activations, norm preserving is they use this thing called the Bjork something or other algorithm, which does like this iterative procedure to find the closest orthogonal matrix to a given matrix. So they use this to try and find weights.
So so the last column would be theirs. Or everything with min max is theirs, right? That's the comparison.
I think, yeah, both of these,
Okay.
both of these columns are theirs, and this is the one where they used orthogonal weights as well as max min.
Oh, okay. And they get, and these are the test errors. Okay. So sort of comparable with Relo. Slightly worse.
I mean,
yeah, they compare against the ResNet. So did they actually use it within like a ResNet architecture?
I don't think so. I think they said that they just worried about like multi-layer perceptrons in this paper, and they have a couple caveats that like you can extend it to more
The
complicated.
table 6 is talking about wide resonance.
Yeah, I'm looking at 6, right?
Well, I don't know.
Maybe then what? Yeah, because what I was wondering, right, with the avoiding the weight decay, do you need the residual layers, right? Can you just do the standard linear layers instead of the residual connections?
Yeah. I'm not sure. Let me jump back to the point where they said this.
Okay, so they turn the convolution into the typical thing of turning it into a matrix multiply.
I honestly didn't read the results section of this paper that carefully.
Yeah, that's okay.
Yeah, honestly, it would probably take a few minutes to figure out what the results were, and we're already 20 minutes over. So
Yeah, right. Okay, cool. Thanks, Ben.
okay. Well, thanks, guys. I definitely learned a few things from your comments today, so I appreciate the input.
Sure. All right. Yeah.
Okay.
Wish you both have a nice weekend. See you.
Thank you. You too.
Likewise.
Thanks.